Alright, so my name is Drew Sheriff, and this is Lab 3, the introduction. So, the purpose of this lab was to model the distance dependence of a bar magnet using GlowScript and compare it to what is being observed in the real world. So, these are the models. On the left, we have like a model of what was being done in real life with my phone and my magnet. And then on the right, we have the GlowScript's computational model. The assumptions are there's no drag, it's a closed system, no outside magnetism at play, besides I guess the Earth. But like we're assuming that there's not like a laptop in front of it or a phone next to it or a fan or something, and we're outside and stuff. The phone magnetism app is accurate. We're praying for that. The main fundamental physical principles in detail are, so we got the Biot-Savart law, which is basically just the magnetic field is equal to the constant thing times I times the cross product of the length and r hat. No, not the length, the velocity. And then under that we got this mu is equal to IA, which is also equal to I pi r squared, obviously. And then we got B ring and B dipole over there. And then they're just derivatives of these other two. And they just give you the magnetic fields of a ring and of a dipole, which in this case is a magnet. So here's a brief preview of the main result. So these are all the numbers that I calculated / measured. So yeah. The system is / was the magnet, and the surroundings are everything else. That's not the magnet. Initial conditions are the magnet is still, two perpendicular rulers are aligned, and the phone is centered on the reading chip using tape, because the phone's long, but the chip's in a certain spot, so you have to find that. So the coding details explain in a clear logical manner. So we got the physical constants, obviously mu over 4 pi, and then we got creating the magnet at the origin, create a function for the magnetic field. We had to input some values over here for the distance. We got all these axes. We have other code that was given to us when we started. And yeah, towards the bottom right, we have arrows. We got a lot of arrows going on. More coding. Seems we got more arrows. And then we do some calculations at the bottom. We're saying what to print like the values of B and the distance and the total net electric field and stuff. So yeah. Similarities and differences between data and model predictions. So the similarities probably that we should garner similar results with these two, because unless we really messed up the real life measurements. But yeah, we're using the same formulas, probably. Same constants. I mean, we put a lot of effort into this lab, so I think the results should be pretty good. Potential source of error are in measuring the length, electronics nearby. Is the app inaccurate? I don't know. Is my phone broken? We'll see. Okay, so what if I hadn't oriented my experiment to compensate for magnetic north and had instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? How would my results have been changed? It would have been changed because it would be wrong. So what if I were to stick two identical magnets together end to end and run the experiment again, how would I expect my measurements to differ? Well, I would expect double the magnets, so double the magnitude of the magnetic field. Anyway, consider subscribing if these help you with your labs, and I'll see you guys around for the next lab.
So after I personally did all of the modeling and experimenting myself, I saw that